Hello, 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 hello. Wonderful. Good morning-ish build stuff. The last couple of years I've been here. It's my favorite conference every year. I've done kind of talks. I've described alternatives as kind of existential dread and software. Now, I think the world is already miserable enough this year, so we're just going to do fun instead. No dread. It's good. It's a change for me. So I'm David, and I'm here to talk you through this weird through line in technology that runs from some kids in MIT in the 80s through to John Carmack, through to Fortnite in the 2020s, and how people's creative urge kind of makes things and making things, and that drive makes just about anything possible with technology. There's a lot of code in this talk. There'll be links at the end, so if you're not taking it all in, don't worry. And we're going to get to building game engines from scratch in a little while. But first, I want to tell you a story about the first game mod ever. So has anyone ever used a game mod? Pretty common, right? Like kind of handful of people. So, all right, in 1981, a couple of MIT students called Doug McRae and Kevin Curran started a company called General Computers. And they released their first video game. It was called Super Missile Attack. Now, what was really interesting about Super Missile Attack was that it was an unofficial sequel to the video game Missile Command. And the two students have programmed it by building an arcade modification board that you could attach to the original arcade cabinet, right? So they basically got a cabinet and reverse engineered it. And they followed this up by making a game called Crazy Otto, using a completely similar technique of reverse engineering the PCBs in the arcade cabinet. And that was to modify Pac-Man. And they accidentally invented game modification on the way. Now, what the mods did is they took the original code in the arcade cabinet and they added new features to the games to increase their difficulty. Because in the late 70s, competitive arcade gaming was a thing. Now, obviously, like all good companies, Atari tried to sue the fuck out of them. But instead, actually, because of a whole cavalcade of litigation, ended up actually hiring them to make games instead. So, as part of their settlement with Atari, they agreed never to sell unlicensed mods again, which I thought was very funny. What then, because of that court deal, what they ended up doing is they sold Crazy Otto, the game, to Midway, who changed the name and released it as Mrs. Pac-Man. So the second ever game mod is something that you've actually probably heard of. So I find this really fascinating because they were probably the first people to get into games the way that the majority of people that get into the games industry today get into games, by taking something that exists and bashing it around and making something cool out of it. Right? So that's cool. And in fact, the early gaming trend of hacking arcade cabinets really did continue through the 80s and into the 90s, often with really weird and unpredictable results. So unless you were born in about 1980, you've probably never played Street Fighter II Rainbow Edition. Now, the funny thing about Rainbow Edition of Street Fighter II, it was a hack in the arcade so popular that Capcom themselves cloned its modifications and eventually released it as Street Fighter II Championship Edition. So the original vendor ripped off the mod and sold it, which is probably another first. And that actually became like the fan favorite version of Street Fighter II. So the truth is that early video games are really self-contained. Each game required mastery of the target platform and its hardware and its gameplay logic and rendering code were all kind of intertwined with the specific systems. And you can kind of see this at the time, right? Because early video game ports in the traditional sense weren't really ports at all. They were generally complete re-implementations of the game on a different piece of hardware. Games rarely shared code. And I think the through line of all this is really a conversation about code sharing. So as games got more and more complicated and bigger business, organizations who were motivated to getting to market quicker started building games on top of games that they previously shipped. So this was most common in, obviously, like direct sequels in game series, where there were just more levels and more features piled on top. But there are some weird anomalies. Like, hey, did you know that Super Mario Brothers on the NES is actually a mod for Excitebike? And the bike momentum physics are Mario's kind of game feel as he runs and has a little bit of a ramp down. So yeah, like it's really cool because as the 80s kind of progressed, lots of companies started to copy that thing, and they started to build like what they used to call game toolkits internally to share code. Now, this led through to the late 80s and early 90s to this boom in what was called game creation kits. Now, some of them were really private, so LucasArts famously had their Scum engine, which I think stood for something like Script Creation Utility for Maniac Mansion, which was the tool set that Monkey Island and Day of the Tentacle and all those classic point-and-click adventure games were built in. Other creation kits were actually launched as commercial products. So when I was a kid in the early 90s, I remember Click and Play. And the most famous example of these game toolkits was Gary Kitchen's Game Maker, which was probably the first. And kits like RPG Maker are now like celebrating their 30th anniversary. So these tools that lots and lots of people got their start making games in are really, really old. At the same while, game engines didn't quite exist yet, because what these toolkits were is they were libraries that you compiled into your game to get an artifact. It wasn't really code reuse or frameworks or engines as you would think about them today. So everything finally changed when id released Doom. Now, I'm sure a lot of people know about Doom. I feel like I have like 3 entire talks that are just, hey, Doom was a really important game. But like in 1993, Doom popularized user-created game mods for the first time, mostly spurred on by its network multiplayer, right? So some commercial licensing of the Doom codebase happened, like specifically to Raven Software, who built Heretic 2, which was a glorified Doom mod. That was produced by John Romero from id Software, and then Hexen. And then Raven then went on to modify the Doom engine to extend its features so that the game that they built was capable of more things than Doom was. id then followed up Doom with Quake, which introduced more than just a level editor kind of game mods. So they pioneered the Quake C programming language. Now, Quake C was built as an extensibility point, a compiled, statically typed language based on C, designed by id for their licensees to change game logic. And id then started realizing that licensing the engine was like a real business, right? So notably, they licensed the Quake engine to Valve, who then turned it into the source engine. The reason it was called the source engine is the folder on the CD that id gave Valve was called Gold Source, and that then just got shortened to the source engine. And then finally, in the parallel universe, Epic Games introduced Unreal and the Unreal Engine in 1998. Following id's licensing model, they kind of saw what id Software were doing, and like, oh, that's a business, great, awesome, we'll do that. And they started licensing their very impressive and still popular Unreal Engine. So the funny thing is, there's like an artifact that's mostly lost to history. So there's a guy called Ken Silverman who built the Build engine that was used for Duke Nukem 3D, which came out the year after, so 1995. Now, it's not really very, very clear where the label game engine came from, but I think the way that history has played out, it's probably that id Software adopted the term engine from Ken Silverman, who called his engine the Build engine, and then Epic copied the name engine when they released their Unreal Engine in 1998. And yeah, because the Quake engine was just called Source at the time. So kind of interesting historical trivia. So I think much of the terminology we have to describe these legacy engines was basically retrofitted onto the 90s in the 2000s. And you know what really happened is all of those id Software game engines ended up getting numbered. So if you're looking for like the Quake engine, it's now called id Tech 1. And there's id Tech 2. I think we're on id Tech 7 now, and Unreal Engine, I think, goes by dates, so 2024 or whatever. But yeah, all of these engines have like a strong lineage back to the 90s, and some of the code is still original in them today. So let's talk about what a game engine is before I show you how to build one. So game engines are, I suppose if we're going to use terms familiar to web programmers and back-end developers, are like just the frameworks of video game development. They provide a programming model that allow you to build games. They tend to come with a lot of optional libraries and modules that are capable of diverse ranges of things depending on what you want to do. And they tend to also have an opinionated model of how you think a game should be constructed. So game engines normally come with modules for things like rendering, graphics, input handling, audio, invoking game logic and user code. But you also find, you know, most of today's big engines will have things like virtual reality modules and maybe mobile phone control modules and device hardware modules. So because of this, engines are often modular, and they will be customized and extended by developers to kind of do the unique parts in their game when people are trying to find the fun. On top of all of that, game engines are normally really useful because as long as the engine code itself can get ported across different platforms like games consoles and mobile targets, your game will come for free, right? So the engine does all the hardware interaction, all the target-specific stuff, and then your game is multi-platform by default. So for reasons we'll get into later, I ended up building a game engine that runs in web browsers over about 10 days a couple of years ago, because I'm stupid. And let's go with this obligatory caveat before we start. There are many valid designs for game engines. These are just some representative examples. So if there's any lifelong game dev in the audience who's like, oh my God, no, a professional engine, well, I know it's fine. It's a conference talk, don't worry about it. So consider this an introduction to the concepts. And I'm basically giving a side eye to YouTube here. Don't at me. Right, so the first concept I want us to talk about is the game loop. So, while not all games run in a game loop, most real-time games do. Now, a game loop runs at a tick rate, which is generally fixed and coordinates the execution of all the other subsystems in an engine. What they generally do is they poll for user input, they increment AI, they execute user-defined logic, and traditionally a game loop would be run at a fixed refresh rate. But over time, a lot of engines have started to divide up the internal tick rate of the game logic from the update rate and the rendering engine's draw rate. And that's the reason that lots of old games, when those two things were stuck in step, would run too fast on newer machines. So then we have renderers. Now, renderers or rendering engines, what they do is they take the game state and they generate the visuals for a game. So they project the data into a UI. Now, 2D renderers are generally concerned with render ordering, sprite animations, camera positioning, and post-processing effects, while 3D renderers tend to deal with 3D asset loading and texture mapping and scheduling calls onto the GPU. Renderers tend to support different low-level graphics APIs, and generally what will happen is that your game engine will target maybe DirectX or Vulkan or Apple's Metal APIs, so you don't really have to think about any of that, and you just deal with game data that you present in the engine's native formats. And finally, we have this concept of game scenes. Now, not all game engines are designed with like a scene graph as the root node, but a scene is like a high-level abstraction over the kind of thing that a game is doing at the time. So a game may have like a main menu and options scene, a real-time gameplay scene, like a loot management scene, and then game behaviors will transition between those different scenes and load level data into them. So a scene to me is like a logical grouping of game behaviors and objects and behaviors. So I'm going to bring some of these concepts to life with a very, very bright example that just lit up the room and I can finally see everybody. We're going to take a look at this very, very famous game, Conway's Game of Life. Hands up if you've seen this before. Okay, excellent. So I won't explain it in super deep detail. So the interesting thing about Conway's Game of Life is it's the world's first zero-player video game. And when we talk about zero-player video games, what we mean is the output is determined by its initial state and some set of entropy or randomness, right? And so the short version to the people that haven't heard of Game of Life, it's a cellular automation simulator written by John Conway. And what happens is, given an initial random state, the game ticks forward, and there are a few rules at play. So it's made up of a grid, and all of the cells get queried on each iteration, and any living cell with fewer than 3 living neighbors dies, as if by underpopulation. Any cell with 2 or 3 living neighbors lives on to the next tick, and then any cell with more than 3 live neighbors dies, as if by overpopulation. So it's basically a simulation of like state changing. Any dead cell then with exactly 3 living neighbors becomes alive. So there's all these different state transitions, and the game basically plays forever. And there's lots and lots of stuff about interesting recurring shapes and randomness. It's super cool. But what I want to do is I want to build a game engine using those systems that we talked about before to capture this. So we're going to do some over-design. So first, we're going to define the most minimal possible engine in a few simple interfaces. So our game engine contains an instance of what I'm just describing as an iRenderer and an iScene. And the scene can be set from the calling code, where we've implemented our game loop, And the game loop just calls update and then render repeatedly, right? So this is a very, very classic game pattern. This is just going to happen every 100 milliseconds using the browser's native request animation frame API, which is just an API to know when the best time to draw to the UI is. You can look it up. So we need some startup code. So we've just got a little HTML page that has a canvas for the UI, along with our startup code that selects that canvas, hands it to the scene. So we create a canvas renderer class and a game engine, and we set our game of life scene as the start of it. So we've just made a little bit of boilerplate kind of structure here. Now, our game of life scene implements this iScene interface, so it has an init, an update, and a render function, along with an iterator that lets us loop over each call sequentially. Now again, don't worry about the real detail of the line by line here. But if we zoom into our update function, here what you're going to see is those are the rules of the game, right? That's the entire actual implementation of Conway's game of life. So we're looping through each cell, evaluating its neighbors and deciding which one should live or die, before finally updating the world state, ready to pass to the renderer to draw to the canvas. And finally, we have our render call. We're just going to loop through the cells again, drawing a black cell or a beautiful teal cell, depending on the current state of life or death. It's a good sentence. The iRenderer is like incredibly dumb right now, and all it can do is draw rectangles. So this is our basic canvas renderer. So all I'm doing here is I'm wrapping the browser's native APIs for drawing on 2D canvases. So you might notice there's a weird thing here where we're inverting the y-axis. And that's because in a web page, you render everything top down. And so topmost, leftmost is kind of 0, 0 in a world. Now, in most games, actually, bottom left is 0, 0. And that's kind of how you would think to render things. So we're just kind of flipping the y coordinate here. And if we run this tiny web app, I say we run this, is that playing? There we go. The game of life runs in our browser. That's it. Right, awesome. So you can obviously write a game of life implementation without all of those game engine abstractions over the top of it, because you can see it's obviously just a loop. But it's a good example to set our framework up so we can build on it for the next couple of examples. Now, while watching the game of life play out in its zero-player existence over and over is the most fun I can possibly imagine having, I think actually most people want a little bit more from their games. So input handling subsystems are used to convert input from gamepads and mice and keyboards through a key map or a button map into desired game actions that you can implement in your game. Now, having this level of abstraction allows you to adapt gameplay from different control mechanisms without having to edit all of your game code, right? So it's really good to have like an input map. It's great for accessibility and all like the esports masters looking to do their own key bindings. Obviously, I'm sure their key bindings are better than mine. So we're going to need a game to rip off for our next example. And this is this excellent little platform game that started as a Flash game in 2010 called Thomas Was Alone. Now, it's a game about a computer mainframe gone wild and malfunctioning AI, and you should play it, but most importantly, lots of its characters are just squares. And you can see in that video, it's pretty simple visually. So I think I'm going to make my own version of that game, given I have a perfect canvas renderer that can only render squares. So we're going to call it David Was Alone. And we're going to start with input handling. Now, building on our glorious Conway's Game of Life engine, David Tech 1, we're going to add a new interface here called an I input device to our game engine. Now, the input device implementations are going to be responsible for mapping input to an object containing currently requested game actions. Thankfully, though, in the modern web browser, you can actually deal with about just any form of input. So you can do your mouse and keyboard. It supports touch. Also, if you get like an Xbox pad and just USB-C it in, you got button maps as well. So we're just going to use the browser's native APIs for that. So here, what we're doing is we're updating our engine to keep track of connected input devices in an array. And then we're going to modify our game loop to pass this collection of input devices to our scene on each update. So the scene can then say, hey, I'm a gameplay scene. What actions are you requesting I do? And then finally, we'll expose a function for our startup code to connect the input devices. So you can see that code there. So this is our keyboard class. All we're doing is we're just wrapping the browser's keyboard event listener APIs and keeping track of which keys are physically held down at the time. So when getCurrentActions is called, we return an actions object with a series of flags set, left, right, jump, standard controls. And you can see here that the same thing can be done using the gamepad API. It's not really much more complicated, but it allows us to use like a standard D-pad and standard buttons via USB. So you have to do some horrible like event listener junk at the top, but the real important bit is that getCurrentActions feature, function at the bottom, which is just checking whether buttons are pressed on the main pad. So finally, in our level scene, we can flatten all of those controller inputs down and move our hard-coded player character whenever a valid action is requested. Now, luckily, David Was Alone is entirely made up of squares. So our existing renderer that can only draw squares works just fine for this game. So up in the top corner, you can see where we've changed the index page to add our keyboard and controller inputs just by calling connect input device at the start. So let's see. There we go. Glorious. David might be able to move, but he's still defying gravity, and he's very, very, very alone. So all we're really doing here is just moving where a square gets rendered, right, on a canvas. It's not truly a character with any behavior of its own yet. It's just a set of coordinates, yet. So at the moment, we don't have a player character in the game. We have a square, and we're changing our XY locations. Now, game engines generally keep track of things that they call entities. And obviously, entities is one of those overloaded terms in software because we use it for everything, right? But just like any other kind of program, really, an entity is just a collection of data, sometimes stored around its behavior. Now, building game entities for behavior lets us keep all of our logic out of the main scene graph, and really it's just an organizational pattern to tidy up our code. So what we're going to do is we're going to add the concept of entities to our code base. First, we're going to create a new draw function in our iRenderer interface. So what this does is it keeps all the display logic abstracted from the game itself. And then we're going to add a couple of new interfaces and something called iUpdatable, which is just there to describe anything in the game world that can be updated or its state can change on each tick. And then we're going to add a game entity that has a physical location in the game world, so X and Y, a width and a height, which itself is updatable, right? And you can kind of see where I'm going here. So let's pick up all that logic for updating our player, and we're going to put it in our new player character entity. And that helps us generalize out that game scene. And the game scene now is just responsible for calling update on every entity stored inside of it, and this is a really common pattern. While it might feel like we're just moving code around a little bit, what this means is that we can now add other types of game entities with different behaviors themselves, and the engine, every tick, will say, hey, update you, do whatever you need to do. Now, another common approach in game development is to implement something called an entity component system. The language is a little tricky here, so I want to take some time talking about terminology. So in traditional object-oriented design, data is co-located with the functions that apply to it. That's what object-oriented programming is, right? So commonly, we model that in languages as classes in OO languages. Now, games in the late 1990s, notably the game Thief the Dark Project, if anybody remembers that, pioneered this idea of an entity component system, which is almost the opposite of OO as a pattern, where the data and the state of the game system doesn't contain the behaviors at all. And there's like some kind of registration table that says, hey, these entities have these characteristics or components. So when you're iterating over the bags of data, pick up these behaviors and apply them in kind of a functional programming-like pattern to these data elements to transform them. So various entity types were basically registered with their associated components, and that was the logic that ran on every tick. Now what this does is it changes our relationship from updating every object in memory to, hey, we're going to run the AI system, and we're going to run the system that processes the logic over any data entity that is in the table for the AI system that needs to have it applied to it. So it's a bit like a visitor pattern for game design, I guess, because game design is often a parallel universe from all the language and the rest of programming. So inspired by this, though it's not explicitly an ECS, in the 2D engines I've built, I like the idea of introducing this concept of characteristics. So what they are, they're attributes that entities can maintain a subscription to that can be used for multiple entities in the game world. So for example, both the player and the enemies can all have the characteristic of physics object. So when the game ticks, I say, hey, every entity, run all your characteristics. And it's a good way, again, to reuse and share common behaviors amongst components in the game. So I like using the word characteristics or behaviors because it avoids the really, really overloaded term component. Because you say component in computer programming and cool, that could be 100 things. So to adapt the engine we're building here, what we've done is we've added an update context that contains our game state. And that game state is passed on each update of the game loop around all of the components and characteristics. So we've modified our game entity to contain an array of characteristics, and we've made being updatable optional on game entities. So of course, we've added this very simple interface for characteristics to implement as well here. Now our level scene is now responsible for triggering the update function on any characteristic that our entities have applied to them, and then optionally calling update on the entity itself if it happens to have its own specific non-generalized piece of logic. So what this does is it slims down our entity class to a minimum while allowing us to share the characteristics between different entities. Now, one of the really nice things about generalizing these behaviors is that we can just apply these characteristics to things specifically like players and enemies can do things like both take damage, right? So you'll notice in this example, I'm just adding an instance of the characteristic to an array here at the bottom. So we've got a characteristic of being controllable, which registers the input controls with this particular, associates them with this particular game object. So while moving our existing behavior into an ECS-like structure might make our code look even a little bit neater, it's also prepared us to add physics to the toy engine, because having physics apply to something can be implemented as a reusable characteristic. Now, physics is hard, yo. I don't know physics and I'm bad at maths. Physics simulations vary wildly between different kinds of game engines. So there are extremely realistic physics simulators in, like flight simulator style games. But also there's much more fun frequently like make-believe physics, like Mario jumping physics, which is floaty and you can kind of go high and sometimes there are double jumps. So for 2D side-scrolling platform games, you don't really want to model real-world physics. It'd be horrible and boring. You want this kind of cartoony physics model. So we're just going to do some Mario physics. So to do Mario physics, first we need to rework how we do controls a little bit. So rather than just forcefully moving our entity's X and Y location, we're going to add some variables to store our current object X and Y velocities, along with defining a weight. And we'll use the weight to work out how fast things are going to fall, and add a flag to work out if we're jumping, whether there's upwards force. So we've set these values in our player character class. There's nothing complicated about this. And we're just going to add this new physics object characteristic that exists after the controllable one. So next, we're going to update our controllable characteristic that instead of moving the absolute location, we're going to increment and decrement the velocity when button key presses happen, along with a maximum capacity so the entity doesn't run off the screen. And we're also going to add some support for jumping by setting the velocity Y value. And the idea is you implement jumping by setting a velocity Y value and you apply gravity to it, and then that number decreases as the player falls. So this is the physics object characteristic. Now, I'm not going to read through every line of this here, but I want to call out a few important pieces. So firstly, what we're doing is we're calculating some collision points that line the bottom pixels and some midpoints of our box. This is important because it gives us collision detection both, it gives us a solid way to find the ground, right? So as we iterate through our objects, we're going to check where those specific points are rather than scanning for every pixel. Then what we're going to do is we're going to apply gravity. So we implement jumping by splitting the amount of time it should take for our object to fall by a 60 frames a second frame rate, and then slowly decrease the upwards velocity of our character until it reaches 0. Combined with the modifications to the controls that set a velocity, that means that when someone presses the jump key, an entity will first move upwards, then slow down and fall in an arc. So it gives you that nice Mario floating jump. Now, actually implementing falling is done when we calculate gravity, so a speed that the entity will fall per game update. If they're ever not on solid ground, we just move them downwards. That's all that happens. And the downward fall increases in speed until they reach a terminal velocity that we set. Now, after we do this, we adjust our X and Y velocities and we apply the movement to the entity, and we shift it by whatever number of pixels that calculation ends up in. So when I say simulating physics, I'm sure a physicist would try and shoot me, but it's fun. So this is what our game engine and scene files look like at this point. And David can fall and jump, but he's also definitely still alone. Okay, we're going to segue to Blue Peter. So in the UK, we have this kids' TV show called Blue Peter. Has anyone ever seen Blue Peter? I appreciate it. We've got a culture, okay, 2 people, 3, brilliant. Okay, so what Blue Peter used to do is they used to make you make little kids' toys out of like used toilet paper rolls and paper bags that your parents had. It was very like 1980s poverty TV, brilliant. And they popularized this one phrase, which was, here's one I made earlier. So they'd set this challenge where you were meant to make a little toy, then they wouldn't show you how to do it, and then they'd bring back this massive mansion that they'd made from toilet paper, and you'd be like, oh, I don't know how you did that, but cool. So if you're going to allow me a bit of a Blue Peter moment right now, I'm going to switch gears as we move on to the next example. So a couple of years ago, during a preparation for a conference booth, I spent 10 days building a game engine that could run in a web browser. The idea was that attendees could walk by and play the game, and they could compete asynchronously. So everyone that day came in and played like a Mario Kart-inspired platform game, where they could run against the ghosts of previous players. So as we move to talking about graphics, I want to introduce you to my magnum opus. It's called I Am Jam. It's a game where you, a humble orange, try to become jam. So here's one I made earlier. Well, actually, I say here's one I made earlier. While I was working on the nuts and bolts of the game engine to make this, Joe actually did all the pixel art. So here's one I didn't make earlier. So this is beautiful, like hand-drawn sprite art. I don't know how this magic works. It's magic to me. It's painting. Other than how great they all look, there's nothing really special about the graphics here, right? It's a couple of JPEGs for background art. It's some keyframes for enemy mice trying to eat our intrepid orange, and some cute clutter objects that we need to pick them up and put them in the game engine so that we can draw more than just squares, right? So we need sprites. Now, sprites are just animation sheets made up of several images that get played. They're little flipbooks, right? So much like our earlier player character entity, in the code base for I Am Jam, we had to design an entity that kept track of the animation frames, and every time, I think it was about every 10th tick, we would flip to drawing the next frame. So we would play a flipbook. We used 2 conventions. We supported animated GIFs, which was a good way to place little like flickering candles in the scene. And we also could do sprite sheets, where we could move through a sequence of images directly. Now, 2D engines generally use flat files, which is all a sprite sheet is. It's all of the different states of an image, where all the frames are laid next to each other, and then your game engine will basically use an offset, and it will take kind of reading from left to right, and it will move and read the data in chunks and rotate around as your character moves. So this is the character class from I Am Jam. Now, it's a little bit busier than the one from David Was Alone. And we have 2 sprites associated with the character, one when they're alive and one when they die. So we have like a death sprite because our orange rots away when it dies. So our drawing logic is also a touch more complicated because the character has state. So we had different sprite sheets, whether they're running or standing still or jumping. Once we work out if we're dead or alive and if we're moving or not, all we do is we call the sprite draw function that does the heavy lifting to flip sprite images. Now, this sprite class is responsible for loading all of the frames of our sprites in sequence, creating mirrored versions for when you're running in the opposite direction. And it uses a low-level image manipulation library called libgif. It's cool. I think it's basically a bunch of code ported from like FFmpeg or something and compiled into the browser. So every 5 game updates, the frame counter will proceed, and then the sprite class draws the next image in sequence. So it's responsible for drawing the image to our canvas directly as well, because the renderer in IMJam is slightly different than the one we built at the start. And it works. Behold, our bounding mouse trying to catch you. Now, let's talk about rendering layers briefly. So in a 2D game, layers are rendered on top of each other to create a sense of depth and ordering. So generally you draw from back to front, kind of like using Photoshop layers. There's the background layer, which is the furthest thing from view, which contains generally static assets and images. A middle ground layer, which tends to contain elements that are closer to the player. So often things like trees and buildings and artifacts. Things that the character can move behind or in front of. And then there's a foreground layer, which is normally the UI that's drawn on top of everything. Now, because our background is one big image, and we're just laying the game entities on top, what we did was we ripped off CSS's Z-index system, so we kind of have an infinite stack of objects that get layered and rendered in order. So you can see an example here where the way our items are overlaid with a slightly translucent foreground jug, and that's so our character could run behind it and you get like a cool occlusion effect. So for this game, we implemented a super lo-fi camera that worked out how to draw our canvas. So based on the player's position in the world, it basically scrolls the background image in the canvas, left and right, making sure not to scroll to the left, to scroll it off the far left or far right of the screen. So when you're at the left of the map or the end of the map, it kind of stops scrolling. And what we do instead is we shift all the entities when we're in those two edge states. Now, traditionally, 2D games are often made up of tile sets and level data, where the tile set is like a palette of reusable chunks that the game can be stamped from. This is really good for memory efficiency, and it's why basically every early video game that was 2D used tile sets, like Sonic the Hedgehog, your classic example. But because we're blessed with modern computers and more than 130 kilobytes of memory, we ain't doing any of that stuff. We don't have a performance budget for this game. So in this 2D game engine, what we're going to do is use bounding box collision and a big fat JPEG. It's great. So each of our entities has a box drawn around it. So a player character and a mouse, and has those collision points. So this is really inexpensive because all the game engine needs to do is when the entities tick, they just check if any of their collision points are inside any of the other entities, and we know that that's a collision. So the reason we've picked those hotspots for collision detection, as I mentioned earlier, is to stop us having to scan every possible pixel. And it also means that the game feels a little bit better when you jump and you slightly hit an enemy. You don't really want it to kill a player. It's no fun, right? We're not building Dark Souls. So people kind of like that forgiving, slightly loose collision detection in games. So if you ever used a real game engine like Unity, you may have heard of bounding box collision detection referred to as box colliders, or the wonderfully vague AABB, axis aligned bounding box collision. Wonderful mouthful. Now, we're using this fun little hack for level geometry collision detection. So at the top here, you can see our whole game map, and at the bottom, you can see a blocked out version of the game map with colors. Now, this is a wonderful hack that works in a video game engine, because all we need to do is, as we're checking our collision points, the exact location on here, we just check that pixel color in the second image, which is loaded invisibly into the browser. And if it's red, you die. If it's black, it's solid. And if it's white, you can walk through it. Right? real clever way, and the reason this is really useful for this kind of game engine is we have enough computers to have the memory, so we don't have to worry about compression and things like that. And the browser has like a get point API in the canvas where we can just take the XY coordinate from one image and check it in the other. So our enemy collision then works on those hotspots. And I think this is a video. There we go. So the easiest way to understand this is this debug mode that I built into the game engine, where you can see the hotspots for the enemies and the bits that we check the downwards collision detection with. Now this I built because I was trying to do the maths and I kept on getting it wrong. And this was a really good way for me to be able to see what was happening. And obviously most game engines will have similar kind of collision debug views. So a lot of 2D platform game feel is really just about how your physics and how your collision works. And also the amount of forgiveness. So things like when you're jumping onto a platform, a lot of game engines will go out of the way to, like, if you missed the jump, no you didn't. Like they give you a couple of pixels of spare leeway. Now, the code to deal with player death exists in the update function on the enemy entity. So on update, it checks if it's currently colliding with the player for each enemy, and if the player is alive. If those conditions are met, and the entity it collides with has a killable characteristic, which in this game means has some health, it calls the logic of the killable characteristic. Now, as we finish, I want to talk about AI briefly. And unfortunately, not the trendy AI that gets you on all the other conference stages, the boring old version of AI. Now, AI in games is like a vast topic that covers lots of different approaches and different programming styles, so it'd be impossible to really go through detailed examples here. The way it's triggered, however, is generally consistent with every other game loop-driven update. So every nth tick, the AI for each entity will step and get given the game state, and then it will make some decisions. Now, let's talk briefly about AI. So most games have some kind of pathfinding AI, that's very common, using either something called navigation meshes, which imagine like a 3D game world with a big net over it, where they navigate based on where the net is. Or common algorithms like the A-star pathfinding algorithm, and then that's normally combined with a series of other techniques. So games like Halo popularized using something called behavior trees, where characters have a set of actions that they can pick from, while an alternative approach called GOAP, goal-oriented action planning, is popular in games with emergent gameplay design. So the idea is that different entities are given different skills and a set of weighted goals, and they pick whatever action to do next matches their goals in priority order. So you'll find like immersive sims use that. It was first popularized by the game Fear, where the enemy AI would flank you, and that's how they implemented flanking. Now, in the games of the late 90s, there were experiments in using neural networks with games like Creatures and Black and White, and generally finite state machines were used in games like Doom and Half-Life, which continues to be the most popular approach for like first-person shooter AI. And then finally, there was a bunch of hybrid AI approaches like the game Left 4 Dead, where they famously implemented an AI game director. And what the AI game director did is it looked at how stressed the player was. So if you weren't doing many game actions and you weren't moving through the map, it would increase the number of enemies that spawned to try and pressure you into behavior, right? So you felt like you were playing against an adversarial AI. Pretty cool. So for completeness sake, I want us to take a look at the AI I wrote for I Am Jam. This is my finest work. It's that. So the AI in this game is really simple. It just runs from left to right and attempts to not fall into holes. So the idea is that an enemy gets an X velocity of 4 pixels per tick in whatever direction it was facing. And every tick, the enemy evaluates if it's about to fall into a hole or not. And if it is, it turns around. That's it. So this means our AI will run backwards and forwards along any platform that it spawns on, but the enemies won't all die before we get to them. So I can't really do a whole talk about playing games without letting you play a game. So hopefully, again, live demo gods, this should work on your phones with touch input or controllers. The right-hand side of your phone is jump, the left-hand side is an invisible D-pad. I'm super proud of how fun this quick little game turned out. It only works in landscape mode. and the artwork is incredible, right? And the event it was used in was a hit because it was fun. Now, there's a huge amount of game engines out there that will help you on your way if you want to do this. I do think that if you're looking to learn about the primitives that go into making a game engine, you'll be much better at understanding the constraints that general purpose game engines impose on your software, right? So would I recommend building a game engine from scratch if you're trying to publish a commercial game? Absolutely not. Like, you don't want to deal with porting to PlayStation and Switch and PC and Mac, right? Use Unity or Godot or Unreal Engine. But if you want to learn some cool stuff, go to Wikipedia and pick from one of the 20,000 free game engines that exist today. So I hope you've had fun learning a little bit about the history of games and engines, and I hope you are maybe inspired to go and do some of this yourself in your free time. Thank you. Have fun.